Hello everyone, welcome to my MLSS poster talk. The title of my poster talk is Tyranny of the Majority, Sparsity Change in the Hidden Layer Reveals a Mechanism of Adversarial Attack. Artificial neural networks have prevailed in applications. Autonomous driving cars use DNNs to recognize street signs. They are also considered to be the best model of feed-forward visual stream. Adversarial attack are examples that differentiate neural network and human perception. One famous example from Goodfellow is, given this image, a well-trained neural network will classify this as a panda, but when a small imperceptible perturbation is imposed on top of this image, the same network would classify this new image as a gibbon. Adversarial attack like this really threatens application security. In this field, there has been this adversarial arms race going on, and a lot of creative ideas are emerging both on attack method side and defense method sides. However, until today, the adversarial problem remains unsolved, and this is partially because as a black box, it is hard to understand really what is going on inside. So the goal of this little project is to look at a simple enough 3-layer feed-forward neural network and try to get an intuition of why they are vulnerable to adversarial attacks. So we train it on MNest images, and the input is MNest, and the hidden layer is a linear transformation of the input plus a bias, and then pass through a standard ReLU activation function to make sure all the hiddens are above 0. Then the output node is calculated as the linear transformation of the previous hidden layer plus a bias, very standard operation, and decision is based on the output layer pass through a softmax to make sure there are probabilities. After we have trained this neural network on MNest images, we take one image and then generates its adversarial attack. So in the adversarial attack case, this neural network would incorrectly classify this image in the bottom as an 8 with a 95% certainty. So what is happening in the output layer to make the network misclassify the second image? So we want to look at how this happens. So notice that the classification is a softmax over the output layer. Over the output layer, and the softmax is a function that doesn't change the order. So what really matters is what is inside the softmax. And we know that for all the hiddens are above 0, which this would imply that for output, in order to study what are the hiddens that contribute to the output node 1, and the output node corresponding to the adversarial class 8, we could group the hidden units into an adversarial supporting set and a ground truth supporting set. So what do we mean by that? For the hiddens which associate with the output node 1, if the weight has a positive value, then this would mean that for the hiddens having a positive weight, their activity will directly contribute to the output class 1 having a higher value in the later layer. And similarly, for the hidden units associated with a positive weight to the adversarial node, their activity will directly contribute to the adversarial node in the last layer having a high value. So after grouping those hidden units into those supporting the adversarial class and those supporting the original class, we can compare the difference of their hidden unit activation when the input is the original image and its adversarial attack. So we have grouped those hidden units into those two supporting groups, and then we can ask what is the difference in their activation when the input is an original image and the adversarial image. So for the hiddens, which are supporting adversarial class, when we plot the histogram of their activities when the input is the original image, their activity seems to be sparser when the input is an adversarial image. So it seems like from the original image to the adversarial image, their activations seem to become denser. And for the hidden supporting the original class, when we plot the histogram of their activities, it seems like when the image is adversarial, their activation becomes sparser. So this is just one observation for one image. The question is, can we generalize this observation across many instances of adversarial attacks? So in order to do that, for each image, we need to use one number to represent the population sparsity. For a couple of reasons, we picked Gini index. So when Gini equals to 0, it corresponds to all the hidden units having an equal amount of activation. And when Gini equals to 1, it corresponds to one hidden unit having all the activation. So this is a popular measure in economics to measure the income inequality. Then we can study the sparsity change of hidden activation population during an adversarial attack. So for the adversarial subpopulation, when compared to the original image, their activity seemed to become denser when the input is an adversarial. And for the original subpopulation, this is also confirming our previous hypothesis that their activity seemed to be sparser when the input is an adversarial image. So when we plot how much those points deviate from the middle line, which corresponding to no sparsity change, we also confirm our observation that there are sparsity and density changes for those two subgroup of population. So to summarize our observation, almost all adversarial attack induce weak and dense activation in the hidden subpopulation supporting the adversarial class. This dense activation can then be summed up by the linear transformation of the later layer of the neural network to increase the activation of the adversarial output unit and change the network's classification. Similarly, adversarial attacks also sparsify hidden population activations supporting the original label, and in turn, reducing the activation of the original output unit. So how does it relate to my title, Tyranny of the Majority? To help you to have a better intuition, let's imagine that the last layer of the network are those two groups calculating the statistics of their lower level feature detectors. And in this case, the blue population are voting for the features supporting class 1, and the red population are voting for the features supporting class 8. When this image comes in, for the feature detectors detecting features for 1, there are a couple of strong activations. But for the feature detectors detecting features supporting class 8, many of them activate weakly. So what would happen is when the later layer tries to sum up the activation of their lower layers, the later layer for the class 8 still sum up to be a higher value compared to the later layer that sum up feature detectors supporting class 1. So this is how this one image is misclassified by the network as class 8 with a very high certainty. So this is pretty much the end of this video. Thank you so much for watching. And in case you have questions or there are interesting things that you would like to discuss, let's chat during the Q&A session. Thank you very much.